The solar system is a study in contrasts, but no world pushes the limits quite like Mercury. It is the swift, silent messenger of the gods, yet its reality is far harsher than the myth. Imagine a world where the day side reaches nearly 800 degrees Fahrenheit, hot enough to melt lead, only for the night to plunge to a crushing negative 290 degrees. This planet isn't just orbiting the sun, it's being hammered by it. Mercury races around our star faster than any other planet, completing an entire year in just 88 Earth days. But its internal clock is bizarrely slow. A single solar day on Mercury is longer than its year. How does a world this small, this close to the solar furnace, manage to harbor ice in permanently shadowed craters? This is a place of absolute extremes, a planet of impossible juxtapositions. We're going beyond the familiar image to explore the science of this scorching yet freezing world. If uncovering these cosmic contradictions intrigues you, consider giving us a gentle like and subscribing for more journeys through the scientific universe. Settle in as we dive into the surprising, brutal reality of Mercury. Living so close to the sun presents an almost unimaginable challenge. The intense heat, the relentless barrage of lethal radiation, and the constant threat of meteor impacts make the inner solar system a profoundly difficult environment. Because of these dangers, and even though Mercury is much nearer to us than giants like Jupiter or Saturn, it remains a world that is relatively underexplored. Despite the difficulties, humanity has successfully dispatched 2 missions to study Mercury. The first, Mariner 10, performed flybys in the 1,970 seconds. Decades later, NASA's Messenger probe made history in 2015 by becoming the first spacecraft ever to successfully enter orbit around the planet. And now, as we speak, a third mission is on its long way. This mission is Bepi-Colombo, a major joint effort between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA. Bepi-Colombo is currently traveling through the constellation Pisces, already over 177 million kilometers from Earth. It is slated to finally arrive at Mercury in December 2025, prepared to carry out a detailed, comprehensive study of the planet's magnetic field, surface composition, and internal structure. As is often said, the journey itself is a crucial part of the process, and Bepi-Colombo's journey is exceptionally long and complex. The spacecraft began its ambitious 7-year trajectory on the 20th of October 2018, lifting off from the French Guiana Space Center. Its path requires it to lay the sun a total of 18 times, incorporating 9 crucial planetary flybys. The first of these gravity assists was a very close pass by Earth on the 10th of April 2020. Bepi-Colombo came within just 12,700 kilometers of our planet's surface, a distance comparable to traveling from Copenhagen to Santiago, Chile. Following that, its itinerary involves 2 flybys of Venus and 6 final flybys of Mercury itself. 3 of these final Mercury approaches are scheduled for next year, specifically in September, December, and January. In total, this mighty spacecraft will travel an astonishing distance of 8.5 billion kilometers. Taking such a long and degrees-udis route was not arbitrary. It was the only way engineers could ensure Bepi-Colombo slowed down enough before attempting to settle into Mercury's orbit. Slowing down is critical. If the spacecraft arrived with too much velocity, it would simply swing past Mercury, and instead of being captured, would be pulled inexorably into the powerful gravitational grasp of the Sunday. Bepi Colombo was designed specifically to build upon and deepen the discoveries made by its predecessor, the Messenger probe. While Bepi Colombo carries many of the same types of instruments as Messenger, it is equipped with more advanced, higher caliber tools capable of collecting a broader range of data. Furthermore, Messenger's orbit was somewhat constrained, with its closest point, or periapsis, situated over Mercury's south pole. This resulted in excellent, detailed mapping of the northern hemisphere, but left the southern hemisphere with significantly less data. Bepi Colombo plans to correct this imbalance by achieving an orbital angle that is much more aligned with the planet's equator, allowing for full, balanced coverage. The Bepi Colombo spacecraft is structurally unique. It is composed of 3 main parts: 2 scientific probes and a propulsion module. These parts were launched and travel together in a combined configuration, which the ESA manages under the name Mercury Cruise System. The first probe, the Mercury Planetary Orbiter, is tasked with studying the planet's surface and interior structure. The second, JAXA's Mercury Magnetospheric Orbiter, is affectionately known as MEO. MEO will focus on investigating the planet's surprisingly weak magnetic field, a scientific puzzle that has challenged researchers for decades. The name MEO was chosen by the Japanese public and means a waterway, symbolizing the scientific progress achieved so far and expressing hopes for a safe journey ahead. These 2 orbiters, MPO and MIO, are stacked onto either side of the Mercury Transfer Module, the Interplanetary Propulsion Unit. This stacked configuration means that most, though not all, of the scientific instruments remain inactive during the long cruise phase. They will only be fully deployed and operational once Bepi Colombo successfully settles into its final orbit around Mercury. At that point, the MPO and MEO will separate from the main transfer module and proceed to study the planet from their respective vantage points. Even while still in its cruise phase, Bepi Colombo has already provided valuable information. The mission's first close encounter with Mercury took place in October 2021. The spacecraft passed a mere 200 kilometers above the planet's surface and returned some stunning, high-resolution images. As it flew past, Bepi Colombo captured a significant portion of Mercury's northern hemisphere. To a casual observer, the images might look similar to our own pockmarked, rocky moon. However, a scientific eye can distinguish features like the Calvino crater, which may hold vital clues about the composition of Mercury's crust. Also visible is the Lamanthe crater, which shows evidence of past volcanic activity. Scientists also observed mysterious, unidentified pockets in the crust, where a compound is actively being lost or sublimated into space, a process whose mechanism remains unknown. These early images powerfully reinforce how truly enigmatic Mercury is and underscore how much remains for us to learn. Another camera aboard the spacecraft provided a different perspective, one that clearly displayed the planet's extensive volcanic history. Features like the Hayden crater, which was once flooded by lava and spans over 250 kilometers, came into view, along with the Pompu facula. This is one of Mercury's many bright spots, likely formed by massive volcanic eruptions that occurred billions of years ago. Even though Messenger had previously confirmed Mercury's volcanic past, it is still astonishing to see that this level of activity left such visible, lasting marks after an incomprehensible stretch of time. Bepi Colombo did more than just photograph the flyby. It captured how the flyby physically felt, We are familiar with the accelerometer in a smartphone, which detects and measures changes in orientation. Scientists mounted a similar, highly sensitive accelerometer onto Bepi Colombo's MPO. This instrument measured the slightest movements and vibrations of the spacecraft as it passed by Mercury, effectively creating a sound map of the encounter. Scientists then translated this data into frequencies that the human ear can actually perceive. This process allowed them to create an audible recording of the flyby itself. Listening closely, one can pick out two distinct sounds near the beginning of the recording. These sounds represent the noticeable changes in solar radiation pressure as the spacecraft first enters and then exits the shadow of Mercury. A final, large clunk sound towards the end is the noise of the PHE bus instrument moving into its designated parking position. During its flyby, Bepi Colombo also gathered data on the magnetic field, which scientists later processed and translated into sound. This particular sound representation is more abstract than the accelerometer recording. Listeners would hear two distinct synthesizers playing simultaneously. The first synthesizer's pitch changes according to the magnitude or intensity of the background magnetic field, meaning a lower pitch indicates a more intense field. The second synthesizer's pitch reflects the variation in the magnetic field's magnitude, where a faster change in pitch signifies a more turbulent magnetic field. The moment of closest approach is marked by a dotted vertical line in the data. After the spacecraft passed this point, a sound akin to a DJ scratching a record appears. A burst of very fast pitch changes. This sound marks the crossing of the magnetosheath, the boundary region where the magnetic field becomes highly turbulent. On the 23rd of June 2022, roughly halfway through its planned 7-year journey, Bepi Colombo crossed paths with Mercury once more. This second approach allowed the spacecraft to focus its cameras on the planet's largest impact scar, the Caloris Basin. Spanning an impressive 1,550 kilometers wide, Caloris Basin stands as one of the largest known impact craters in the entire solar system. It is believed to have been formed around 3.9 billion years ago by the collision of a massive comet, asteroid, or other celestial body. Highly reflective patches of hardened lava on its floor make it easy to spot as the bright semi-degrees Euler area visible just below the magnetometer boom in the images. This second flyby provided beautifully detailed images of Mercury's craters, revealing features with striking clarity. One image showed the Hyani crater, which is set within smooth volcanic plains, possibly near an ancient volcano. This area is specifically targeted for closer examination once Bepi Colombo finally settles into its orbital phase. Almost exactly a year later, on the 19th of June 2023, Bepi Colombo executed its third close approach, swooping in from a height of just 263 kilometers. The images captured during this flyby included the 600-kilometer-long Beagle Roops. This is one of the many lobate scarps, stepped, curved cliffs on Mercury's surface, a feature first photographed by the Messenger mission in 2008. Mercury is unique among the planets in our solar system, second only to our moon, in exhibiting this specific type of tectonic feature. A lobate scarp forms when the interior of a planetary body cools and shrinks. This global contraction forces the surface crust to buckle and fracture, resulting in a thrust fault, which is the geological name for a lobate scarp. Beagle Rupes is particularly noticeable because its curvature is more pronounced than other scarps found on Mercury, offering geologists rare insights into the planet's complex tectonic past. As a direct result of this third Bepi-Colombo flyby, a large 218-kilometer wide peak ring impact crater was formally named Manly in honor of the 20th century visual artist Edna Manley. The crater's original basin floor was later flooded and smoothed by lava, giving its interior a visibly gentle texture. From orbit, Bepi-Colombo will study Manly Crater further, aiming to measure its carbon composition and detect other minerals present to piece together more details of Mercury's geological history. The most recent flyby saw Bepi-Colombo glide past Mercury, taking a series of final, close-up images. At a distance of 236 kilometers from the surface, the spacecraft appeared to embrace the planet as a farewell gesture. Scientists back on Earth now face a waiting period of 16 months before the next set of flyby images arrives. These flybys offer more than just visually impressive pictures. They also reveal crucial information about the planet's surrounding particle environment and its magnetic boundaries. One of the instruments aboard the MPO probe is PFES, which stands for Probing of Hermian Exosphere by Ultraviolet Spectroscopy. PBIS uses the UV light emitted from Mercury's exosphere, the planet's extremely thin, outermost, and only atmospheric layer, to determine its composition, structure, and how it interacts with the surface. PBIS achieves this by detecting specific light emissions within the ultraviolet spectrum, ranging from 55 to 350 nanometers. By capturing these emissions across the full spectrum, the instrument helps scientists figure out the composition of the exosphere and how its constituent particles are spread out. As Bepi-Colombo emerged from Mercury's shadow, PHEBIS successfully detected the presence of hydrogen and calcium. This confirmed earlier findings from the MESSENGER mission, which had already established calcium's presence in the planet's exosphere, particularly concentrated around the equator and on the night side. Interestingly, this distribution pattern is the opposite of what is observed for sodium and potassium, which tend to concentrate more readily around the poles. Once Bepi-Colombo is firmly in orbit, PBIS will be able to transmit much more detailed analyses of the exosphere's composition and dynamics, including how its characteristics shift based on location and time. Speaking of MESSENGER's discoveries, that mission famously found evidence of ice on Mercury's North Pole. Bepi-Colombo is tasked with continuing this work by intensifying the search for water ice in the permanently shadowed regions within high-latitude craters. Mercury is the only planet in our solar system, other than Earth, known to possess a global magnetic field. This field is generated by a dynamo effect, originating from the movement of liquid iron within the planet's core. However, Mercury's magnetic field is remarkably weak, measuring only about 1.1% the strength of Earth's magnetic field, which makes the way it is generated a source of intense scientific fascination. A core goal of the Bepi-Colombo mission is to achieve a much better understanding of this field. So far, only the magnetic activity of the Northern Hemisphere has been comprehensively mapped by NASA's MESSENGER mission. Scientists are counting on Bepi-Colombo to illuminate the dynamics of the planet's magnetism in the Southern Hemisphere. This magnetic field is profoundly important. By understanding it, scientists hope to shed light on Mercury's earliest origins, its evolutionary path, and the current state of its interior. The two orbiters, MPO and MEO, will travel through different regions of Mercury's magnetosphere at different times. They will simultaneously measure how the magnetic field changes across both time and space, and its direct relationship to the powerful solar wind constantly flowing from the sunday. All the new data collected by Bepi-Colombo will eventually be compared with the existing global magnetic field models derived from the MESSENGER mission. This comprehensive effort aims to build the most accurate picture yet of Mercury's magnetic field, which could unlock revealing insights into the planet's elusive history. As we anticipate Bepi Colombo's next flyby in September 2024, the journey to fully understand Mercury continues. The spacecraft is preparing for its next major maneuver, a long-duration solar electric propulsion thruster arc scheduled to begin in early August and last until mid-September. These continuous thruster arcs, combined with the strategic planetary flybys, are essential for Bepi Colombo to counteract the enormous gravitational pull of the Sunday. This process of continuous braking is the only feasible way to successfully insert the spacecraft into orbit around Mercury when its arrival window opens. Once orbital insertion is achieved in December 2025, the primary scientific exploration will begin. Mercury's heavily cratered surface holds a 4.6 billion year record of bombardment by asteroids and comets. This impact history, along with the planet's unique tectonic and volcanic curiosities, will help scientists decipher the planet's place in the evolution of the entire solar system. Bepi Colombo is currently scheduled to remain in orbit around Mercury for 1 Earth year, with a possibility of being granted an extension for a 2nd year if the mission remains successful. Scientists hold high hopes for Bepi Colombo, aiming to study Mercury like never before. They want to understand everything from its elemental makeup to its internal structure, from its incredibly thin atmosphere to its magnetic environment. Ultimately, the goal is to unravel not just Mercury's past, but also the early history of other inner rocky planets, including Earth. Until Bepi Colombo achieves orbit, we still have a few more flybys to look forward to, promising more of those profound, haunting images for us back on Earth. Imagine yourself standing on Mercury's surface, but not the searing, sun-blasted daytime inferno we usually picture. Instead, you are there during the planet's unbelievably long night. The sun dipped below the horizon weeks ago, and it won't reappear for weeks more. Above you, the stars are brilliant and sharp against a flawless black sky, entirely untouched by any atmospheric haze. The ground beneath your heavily insulated boots is frozen and rigid, steadily radiating the day's immense heat out into the vacuum of space. It is a silent, completely desolate landscape. But you have brought special equipment for observation, not just for survival. You point a sensitive light detector, tuned to a specific wavelength, toward the anti-solar point, the direction exactly opposite where the sun is lurking below the horizon. And there, you see something faint, almost ethereal and unbelievable. Stretching out from the planet, reaching impossibly far into the blackness, is a ghostly, elongated glow. It's a whisper of light, entirely invisible to the unaided human eye. This delicate structure, millions of kilometers long, trails behind this tiny, battered world like the train of a spectral gown. Mercury, the seemingly bland little rock closest to the sun, is doing something profoundly strange in the dark. It is venting a tail into space. This tail is made not of the gas or dust we associate with comets, but of something much more specific and intriguing: sodium atoms. We're about to explore one of the solar system's most subtle and surprising phenomena: the vast, invisible sodium tail of Mercury. We'll investigate how this bizarre feature was discovered, look into the complex processes that create and shape it, and understand what this ghostly appendage tells us about the innermost planet and its violent relationship with the Sunday. When we think of planets with dramatic, unique features, Mercury is rarely the first that comes to mind. It's often categorized as the smallest, the speediest, and the tiny, cratered world baking closest to the Sunday. But in 2001, this perception fundamentally changed. Scientists had been using specialized sodium filters to observe Mercury since the mid-1980 seconds, when they first confirmed the presence of sodium in the planet's exosphere. This is exactly what a team at the McDonald Observatory in Texas was doing when they noticed something strange, a faint glow that extended far beyond Mercury's tiny, recognizable disk. Initially, the scientists doubted their own eyes, suspecting an equipment malfunction or an error in data processing. However, after extensive checking and rechecking, the astonishing truth became undeniable. Mercury was trailing an enormous structure through space, a tail of sodium stretching almost 2.5 million kilometers behind it. To give that perspective, the tail is 700 times the width of Mercury itself. The discovery was a humbling moment for planetary science. Mercury is one of our closest cosmic neighbors. We've been observing it since ancient times, and have even sent two spacecraft, NASA's Mariner 10 inches, the 1972, and Messenger in the 2000s, to visit it. Yet, this colossal feature remained completely undetected until the 21st century. The discovery was significant because it forced a reevaluation of what kinds of objects in our solar system can possess a tail. Suddenly, Mercury was no longer just a bland, cratered sphere, but a planet with a dynamic feature that rivaled the most spectacular comets. So, how exactly is Mercury's tail different from a comet's? And why is this planet specifically trailing sodium? The answer is a fascinating result of Mercury's unique proximity to the Sun, its composition, and the Sun's fierce influence. Comets are often described as space snowballs. They are primarily composed of ice, which undergoes sublimation, turning directly from solid ice into gas as the comet nears the sunday. This process leaves behind a distinct trail of ionized gas and dust particles. Mercury, by sharp contrast, is a rocky planet with essentially no widespread ice. While scientists believe there may be stable ice hidden in permanently shadowed craters at the poles, these frozen deposits remain stable precisely because they never receive direct sunlight and, therefore, do not sublimate into the exosphere. This means Mercury's tail is not formed through the sublimation of ice. It is made of sodium, and to understand why that is, we need to focus on its environment. At its closest point to the Sun, known as perihelion, Mercury comes within 47 million kilometers of our star. At this distance, it is exposed to solar radiation up to 10 times more intense than what reaches Earth. The solar wind is absolutely torrential here. Imagine a constant stream of charged particles flying from the Sun at 1.6 million kilometers per hour, hitting the planet directly. When these particles strike, they physically knock atoms off Mercury's surface in a process called sputtering. Think of several magnets lightly stuck to a refrigerator door. They stay put on their own. Now, imagine throwing a bouncy ball at the door. The energy from the impact spreads out, shaking the magnets. If enough energy reaches a weakly bound magnet more energy than what holds it in place, it'll pop off and fall. That analogy describes what happens in a sputtering collision cascade. Ions from the solar wind shower Mercury, creating high-energy impacts that dislodge the weakest linked atoms from the planet's surface. It turns out that one of the most weakly bound elements on Mercury's surface, making it easiest to knock off, is sodium. Data gathered by the Messenger spacecraft confirm this. During periods when solar wind activity is high, these charged particles raining down on Mercury's surface lead to a 50% increase in sodium group ions in the planet's atmosphere. This correlation clearly indicates that stronger solar wind activity enhances these surface particle interactions, resulting in a greater release of sodium that feeds into Mercury's exosphere and subsequently its tail. But the solar wind isn't the only mechanism at work. Mercury is also constantly bombarded by micrometeoroids. Without a protective atmosphere to slow them down, even dust-sized particles strike the planet with tremendous hypervelocity force. These tiny space rocks instantly vaporize surface materials upon impact, releasing still more sodium atoms into the environment. We are, in essence, watching a process of space erosion, a planet slowly disintegrating over billions of years, right here in our cosmic neighborhood. Some researchers have noted temporary increases in the tail's brightness that seem to correspond with times when Mercury is predicted to pass through denser streams of interplanetary dust. This dust likely originates from sources like the debris trails left by Comet Encke. Such passages would significantly boost the contribution from the micrometeoroid impact vaporization, temporarily increasing the amount of sodium injected into the exosphere and subsequently fed into the long, visible tail. The force that shapes and stretches Mercury's sodium tail is not the solar wind blowing it back, which is the primary driver for a comet's faint blue ion tail. Instead, the dominant and consistent force sculpting Mercury's structure is solar radiation pressure. This phenomenon is a fundamental concept in physics, subtle in its action on Earth, but immensely powerful over the vast, empty distances of space near the Sunday. To understand this, we must remember that light, while massless in the traditional sense, is composed of particles called photons, and these photons carry momentum. When a sodium atom, now part of Mercury's sparse exosphere, absorbs an incoming photon of sunlight, it instantly receives a tiny physical push. This push is always directed straight away from the sun, in the exact direction the photon was traveling. Immediately after absorption, the atom quickly re-emits a photon, but this re-emission happens in a random direction, meaning the recoil is, on average, negligible and doesn't cancel out the initial push. The atom is then immediately ready to absorb the next photon streaming from the Sunday. This continuous, unrelenting cycle absorption, momentary push, and re-emission acts like a gentle, perpetual acceleration mechanism. It functions as a steady, focused stream of energy, constantly nudging the sodium atoms away from our star. You can visualize each sodium atom as a microscopic, nearly perfect solar sail. These countless tiny sails are being persistently pushed by the sheer energy of sunlight, far exceeding the effects of a typical gas or dust trail. This continuous, focused pressure accelerates the sodium atoms in the anti-solar direction, a path directly opposite the Sunday. Crucially, this force is strong enough to overcome the tug of Mercury's already weak gravity, stretching the atoms out into the colossal, elongated tail structure observed from Earth. This physical process ensures that the tail reliably points directly opposite the Sun, regardless of Mercury's precise position in its orbit. The difference between the solar wind, which consists of massive, charged particles, and solar radiation pressure, which consists of massless photons, is the key to understanding this specific planetary feature. Despite the immense scale of this sodium tail stretching millions of kilometers, it is completely invisible to the human eye. So, how did scientists find this colossal, hidden structure? The key lies in the unique way that sodium atoms interact with light. When sodium atoms absorb energy, they transition into an excited state, meaning one of their outermost electrons temporarily jumps to a higher energy level. When this electron instantly falls back down to its normal or ground state, it must release the excess energy, and it does so by emitting a photon of light at a very precise, distinct wavelength, 589 nanometers. Light at this specific wavelength has a characteristic amber-yellow color that is familiar to us. It is the signature glow of sodium vapor lights used in older streetlights and some highway lighting. This constant emission process is happening everywhere within Mercury's tail. However, the tail's glow is astonishingly faint. Because Mercury is so close to the sun, this faint emission is entirely drowned out by the sun's intense, blinding glare, making it impossible to see with standard astronomical telescopes or the unaided eye. To reveal the tail, astronomers must use specially designed optical instruments called sodium D-line filters. These highly specific filters are engineered to isolate and transmit only the light at precisely the 589 nanometer wavelength. By effectively acting as a highly selective gate, the filters block nearly all other wavelengths of light, including the overpowering white light of the sun, allowing only the faint, specific, amber-yellow glow of the sodium atoms to stand out clearly against the black background of space. This filtering process is the technological triumph that allowed scientists to finally confirm the existence, extent, and dynamic nature of the sodium tail. Mercury's sodium tail is not a static object. It is highly dynamic, changing dramatically throughout the planet's 88-day orbit around the Sunday. Mercury's orbit is unusually elliptical. It is stretched out, not degrees Euler, which means its distance from the sun varies significantly. When the planet reaches perihelion, its closest point to the sun, at about 47 million km, the intensity of solar radiation and the solar wind both skyrocket. This dramatically increases the rate at which sodium is ejected from its surface via sputtering and vaporization. Intuitively, one might expect the tail to reach its peak brightness at this perihelion point, since the forces driving its creation are at their maximum. However, astronomical observations revealed a surprising fact. The peak visibility of the tail actually occurs about 16 days after Mercury has passed perihelion. This delay is due to a fascinating and precise interplay of the planet's orbital speed and a core principle of light known as the Doppler shift. Because its orbit is so stretched, Mercury's orbital speed is also highly variable, ranging from about 39 kilometers per second when it's farther away, up to an incredible 59 kilometers per second when it's closest to the Sunday. Scientists observed that Mercury achieves its maximum radial velocity, its top speed moving away from the sun exactly 16 days after passing perihelion. This specific orbital timing creates the absolute best conditions for the sodium tail to become most observable from Earth. But why would maximum recession speed cause the tail to become brighter? The answer lies in the interaction between Mercury's sodium atoms and the 589 nanometer sodium light being emitted by the sun itself. When we look closely at the spectrum of light coming from the sun, we can see thin, dark lines called Fraunhofer absorption lines. These lines indicate specific wavelengths of light that are being absorbed by elements present in the sun's own atmosphere before the sunlight is emitted into space. Crucially, the sun's atmosphere contains sodium. This atmospheric sodium absorbs all the 589 nanometer sodium light, creating a dark gap, a kind of void in the spectrum that travels toward Mercury. If the tail were stationary, there would be very little 589 nanometer light available for the sodium atoms in the tail to absorb and re-emit. This is where the speed of Mercury changes everything. The faster Mercury travels away from the sun, the more the entire sunlight spectrum is subject to the Doppler shift. This shift causes the wavelength of the light to be stretched or shifted toward the redder end of the spectrum. When Mercury is moving at its maximum speed away from the sun, the entire light spectrum, including the dark Fraunhofer absorption lines, is Doppler shifted. This means that the sodium-specific light that was previously blocked by the sun's atmosphere is now slightly shifted out of the absorption line, making that 589 nanometer light available to the tail. This unblocked sodium light now reaches Mercury's exosphere, and the sodium atoms in the tail can vigorously absorb and then rescatter it. The result is a significant and temporary surge in the tail's brightness, making it clearly visible to telescopes on Earth. To successfully observe Mercury's spectacular sodium tail, astronomers must time their viewing not only around the dynamic 16-day window after perihelion, but also factor in 3 essential astronomical alignments. First is elongation. Mercury must be at a sufficient angular separation from the sun in Earth's sky, ensuring the tail's faint glow isn't completely washed out by the sun's overwhelming glare, a frequent problem when attempting to observe anything near our star. Second, the solar alignment must be favorable, meaning the planet cannot be in conjunction, hidden directly behind the sun from our perspective, nor positioned too close to the sun's disk. Finally, the viewing angle is crucial. Mercury must be at the perfect orbital angle for Earth-based telescopes to obtain a clear line of sight along the tail's long, anti-solar direction. This precise alignment, which coordinates Mercury's orbital mechanics with Earth's line of sight, occurs only during very specific, relatively rare periods, sometimes separated by years. The initial discovery by the scientists at McDonald Observatory was, in many ways, an incredible stroke of observational luck, emphasizing the delicate timing required for such a finding. Some of the most detailed images of Mercury's sodium tail have been captured using specialized instruments called coronagraphs. These instruments block the sun's direct light with an opaque disk, similar to how the moon blocks the sun during a total solar eclipse. This technique allows the faint glow of the tail to become visible even when Mercury is relatively close to the sun in our sky. Every successful observation represents a significant triumph of careful astronomical planning and technical precision. These rare, precious glimpses showcase a feature that dramatically changes its form, stretching, shortening, brightening, and dimming in a cosmic dance governed by atomic physics and orbital mechanics. Finally, while the 589 nanometer light from sodium is the easiest to detect and forms the most prominent part of the visible tail, other alkali metals have also been confirmed to contribute to Mercury's dynamic exosphere and tail structure. Potassium and calcium atoms are also released from the surface through the same sputtering and micrometeoroid vaporization processes, forming faint, secondary components of the tail. Sodium's specific spectral characteristics, its high scattering efficiency and proximity to the readily observable part of the visible spectrum, simply make it the most prominent and easily tracked component, providing scientists with the perfect tracer to study the dramatic effects of solar activity on the innermost planet. The story of the sodium tail stretches far beyond Mercury itself. This subtle, dynamic feature has unexpectedly provided a critical window into fundamental processes occurring throughout our solar system, and, crucially, around distant stars. Firstly, The tail offers us a glimpse into planetary evolution. While the current, ongoing rate of surface material loss from Mercury is far too small to significantly change the planet on human timescales, over vast stretches of geological time, billions of years, this continuous process could potentially affect its overall surface composition. It represents a slow, relentless mechanism, gradually depleting easily liberated elements like sodium and potassium from the planet's outer layers. By rigorously studying the physics behind this process on Mercury, we gain the knowledge necessary to infer what might be happening to older, airless, rocky planets in other stellar systems, allowing us to better understand their long-term life cycles and evolution. Secondly, and perhaps most excitingly, this discovery holds profound implications for exoplanet research. We know that many star systems host hot Jupiters, massive planets that orbit extremely close to their parent stars. If tiny Mercury, only 4,880 kilometers wide, can generate a dynamic 2.5 million kilometer tail, these massive, close-orbiting giants are likely to sport even more dramatic atmospheric features. Such planets are expected to be shedding significant atmospheric or surface mass through similar, highly energetic mechanisms. The specific, high-precision detection methods developed by astronomers to successfully isolate and study Mercury's faint tail are now being adapted and applied to the search for similar phenomena around distant worlds. By carefully looking for the distinctive spectral signatures of elements being stripped from exoplanets, astronomers are beginning to gain unprecedented new insights into their chemical composition, temperature, and environment. This is not mere speculation. Similar sodium tails have already been detected around our own moon, confirming that this phenomenon may be a common process around most airless bodies that are heavily exposed to the constant outflow of the solar wind. Mercury's visible, yet ephemeral, sodium tail represents a perfect natural laboratory for studying planet-star interactions across the universe. By achieving a deeper understanding of this local phenomenon, we gain crucial quantitative insights into exactly how stars exert influence, shape, and slowly erode their planetary systems over billions of years. The Bepi-Colombo mission has now completed 6 rapid flybys of Mercury and is scheduled to successfully enter orbit in December 2025. Once there, it will spend at least 1 Earth year studying Mercury's internal composition and, critically, observing its extensive exosphere. This orbital vantage point will provide data on the sodium tail in unprecedented detail, promising significant new discoveries about this fascinating and important cosmic feature. This elusive tail reminds us that even after centuries of astronomical observation and 2 prior space missions, fundamental discoveries about our closest cosmic neighbors are still being made. The universe is a place that never stops surprising us, and often, all we need to do is keep improving our tools and continue looking closely. Everyone knows the name of the first planet in our solar system, Mercury. It was easily visible in ancient times and was named for the Roman messenger god. Its existence has been known for thousands of years. It isn't hidden in darkness. Thanks to its position right next to the sun, it is constantly bathed in brilliant, overwhelming light. And yet, ironically, it remains the least explored of the 4 inner, rocky, terrestrial planets, having only been visited by 2 dedicated space probes in all of our spacefaring history. Why is this world, known for millennia, so lightly explored? Is it simply uninteresting? What do we truly know about Mercury's fundamental characteristics, its deep history, and how have we managed to piece together that knowledge? When most people consider the physical characteristics of Mercury, they correctly picture the planet closest to the sun, a giant rock suspended in space. While that's an accurate starting point, the reality of Mercury is far more complex and compelling than that simple image suggests. For example, when looking at Mercury, its appearance often reminds observers of our moon. However, when seen in its true color, a combination of elements revealed in high-resolution imaging, the first thing you notice is that it actually has a distinct brownish-gray color, moving beyond the simple shades of uniform gray that characterize the moon. More surprising than its color is its internal composition. Did you know that Mercury is composed of approximately 70% metallic material and only about 30% silicate material? This makes the planet significantly more metallic than rocky overall. Because of this high metallic content, Mercury's density is the second highest in the solar system, at 5.427 grams per cubic centimeter. This density is only slightly less than that of Earth, which holds the record at 5.515 grams per cubic centimeter. If Mercury happened to be the same size as Earth, its surface gravity would be nearly identical to ours. However, being the small size that it is, Mercury's surface gravity is only 3.7 ms2. For comparison, this means that the surface gravity on Mercury is only slightly less than the gravity on Mars. Given that Mars is a much larger planet than Mercury, this fact alone speaks volumes about the extreme density of Mercury's interior. Before moving on from the planet's size, it is worth noting one last comparison. Two giant moons in the solar system, Ganymede, Jupiter's largest moon and the solar system's biggest, and Titan, Saturn's largest moon, are both physically larger in diameter than Mercury. Yet, because of Mercury's immense density, its total mass is significantly greater than the mass of either Ganymede or Titan. If you examine Mercury's surface closely, its general appearance is similar to that of our moon, dominated by extensive plains which resemble the Maria on the moon and heavy, pervasive cratering. This extreme saturation of impact craters strongly suggests that the planet has been geologically inactive for billions of years, a condition known as a frozen or dead world. However, it was clearly geologically active at one point in its distant past, as evidenced by a number of distinctive features. One of the most notable features of Mercury's surface is the presence of many narrow ridges, extending up to several hundred kilometers in length. These are the lobate scarps that we discussed earlier, which are essentially large-scale thrust faults, indicating that the planet's entire crust contracted and shrunk. We will discuss the details of this planetary contraction later. One of the most distinctive and visually striking features on Mercury is the colossal Calorus Basin, a huge impact structure with a diameter of 1,550 kilometers. The impact event that created the Calorus Basin was so unbelievably powerful that it is believed to have triggered lava eruptions across the planet and left a concentric ring of raised terrain over 2 kilometers tall surrounding the central impact crater. Intriguingly, located at the precise antipode, the exact opposite side of the planet from the Calorus Basin, is a large region of unusually hilly and chaotic terrain, known fittingly as the weird terrain. When compared visually to the smooth, cratered plains surrounding it, the name clearly describes its jumbled appearance. Scientists believe the seismic shock waves generated by the colossal impact that formed the Calorus Basin traveled straight through the planet's core, meeting and converging on the exact opposite side, violently disrupting and uplifting the crust to create this unique, bizarre landscape. What is the actual environment like on the surface of Mercury? To begin with, the surface temperature across the planet varies immensely. It can range from a blistering high of over 400 degrees Celsius, 750 degrees F, in the direct sunlight, to a brutal low of negative 173 degrees Celsius, negative 280 degrees F, in the shadow. At the poles, the temperature never rises above about negative 93 degrees Celsius. This is because Mercury has virtually no atmosphere to degrees-ulate heat or retain it. Consequently, there is an enormous difference between the equator and the poles. This massive temperature variation is also profoundly affected by its unique orbit and rotation, a topic we will explore in detail. The subsolar point, the spot on the surface directly facing the sun, can reach around 400 degrees Celsius, hot enough to melt lead. Meanwhile, the dark side of the planet, which has been facing away from the sun for a prolonged period, maintains an average temperature of approximately negative 63 degrees Celsius. This constant, dramatic shift between searing heat and crushing cold makes Mercury the planet with the most extreme temperature swings in the entire solar system. Mercury is small and consistently hot due to its proximity to the sun, and these two factors prevent its gravity from retaining any significant, dense atmosphere over long periods. Because it lacks a thick, insulating blanket of air like Earth, Mercury is unable to trap or degrees-ulate the enormous amount of heat it absorbs from the sunday. This explains the drastic temperature swings. The side facing the sun is brutally hot, while the dark side of the planet, where heat is rapidly radiated into space, becomes crushingly cold. However, Mercury does possess an exosphere, which can be thought of as an extremely thin, atmospheric-like volume surrounding the planet. In an exosphere, molecules are still gravitationally bound to the planet, but the density of gas is so incredibly low that the molecules almost never collide with each other, meaning it cannot behave like a typical gas or wind. This volume of space is often considered the point where a planet's atmosphere truly merges with the vacuum of space. For comparison, Earth also has an exosphere, but it only begins at an altitude of about 600 kilometers above the surface. As seen in images taken by the MESSENGER probe, the exosphere is visibly affected by the solar wind. The stream of charged particles from the sun constantly impacts the planet, physically ripping certain atoms out of the exosphere and carrying them away into space. This flow of material, which includes elements like sodium, potassium, and calcium, creates the planetary tail that trails behind Mercury. In fact, every planet in the solar system, to some extent, has this kind of dynamic exosphere and a resultant tail. In Mercury's case, its exosphere is highly unstable. Atoms are continuously lost to the solar wind and radiation pressure, but they are also continuously replenished from a variety of sources, which include the sputtering of surface material by solar wind ions and the vaporization caused by countless micrometeoroid impacts. Despite its scorching daytime temperatures, NASA has confirmed that craters located near the North Pole of Mercury contain deposits of water ice. This ice survives because the floors of these deep craters are permanently shielded from direct sunlight, allowing temperatures to remain frigid, low enough to preserve the frozen water. Mercury also possesses a feature that the planet Mars completely lacks: a genuine magnetosphere, or a global magnetic field that in degrees less the planet. This field is generated internally, likely due to the movement of liquid iron in its core, creating a dynamo effect similar to Earth's. However, Mercury's magnetic field is remarkably weak, measuring only about 1.1% the strength of Earth's magnetic field. Nevertheless, it is still strong enough to deflect a significant portion of the solar wind around the planet, preventing the most harmful particles from directly striking the surface. This deflection helps to protect the surface materials and regulate the loss of the exosphere. Mercury has the most eccentric orbit of all the major planets, meaning its orbital path is the most stretched or elliptical. Its distance from the Sun ranges dramatically, from a close approach of 46 million kilometers at perihelion to a distance separation of 70 million kilometers at aphelion. Understanding Mercury's movement requires bearing in mind two intertwined motions. First, it takes about 88 Earth days to complete one full orbit around the Sun, which defines its year. Second, it has a unique 3-to-2 spin-orbit resonance. This means that the planet completes exactly 3 full rotations around its own axis for every 2 complete orbits it makes around the Sunday. To put this in human terms, it takes about 59 Earth days for Mercury to rotate once on its axis. This is called a sidereal day. Coincidentally, this 59-day rotational period is almost exactly half of Mercury's synodic period, the time it takes for Mercury to return to the same position relative to both Earth and the Sun, which is 116 Earth days. This means that between 2 consecutive alignments of Earth and Mercury, the planet rotates exactly twice on its axis. Historically, this near coincidence caused a significant problem for early astronomers. Because Mercury orbits so closely to the Sun, it was extremely difficult for ground-based telescopes to get a good, consistent look at it for most of its year. The planet only became visible when it moved far enough away from the Sun's glare in our sky. When astronomers finally achieved a good viewing angle from Earth, they would observe the visible face of the planet. Then, 116 days later, when the planet returned to that prime observational alignment, they would look again and see what appeared to be the exact same face. Based on this repeatable observation, astronomers believed for the longest time that Mercury was tidally locked to the Sun, meaning they thought it rotated once for every orbit, always keeping the same side facing the Sun, much like our moon does with Earth. What early astronomers failed to realize was that Mercury had rotated precisely twice on its axis during that 116-day window, meaning they were observing the same face during the same phase of its rotation cycle. It wasn't until advanced radar observations of the planet were performed in the 1,960 seconds that scientists finally discovered that Mercury does, in fact, rotate slightly faster than it orbits, confirming the unusual 3-to-2 spin-orbit resonance. This 3-to-2 orbital resonance leads to a truly bizarre effect if you were to stand on the surface. Because of the way the planet's rotation and orbital speed interact, one full day from sunrise to the next sunrise, what is called a solar day on Mercury, lasts for exactly 2 Mercurian years. Standing on Mercury, a single cycle of day and night would appear to unfold like this. Imagine the Sun rising relatively quickly above the horizon. As it approaches the midday point, its apparent movement across the sky begins to slow down. Then, as it nears perihelion, Mercury's closest point to the Sun actually appears to stop in the sky, and then briefly starts moving backwards along its path, before finally resuming its normal forward motion toward sunset. This entire sequence, from one sunrise to the next, takes 2 full orbits around the Sunday. The Sun appears to move backward in the sky because of a momentary balance of speeds. Approximately 4 Earth days before perihelion, the speed at which Mercury is traveling along its highly elliptical orbit momentarily equals the speed at which the planet is rotating on its axis. At this precise moment, the Sun's apparent motion appears to stay stationary to an observer on the surface. At perihelion itself, Mercury's orbital speed temporarily exceeds its rotational speed. Since the orbital motion dictates the direction of the Sun's movement relative to the ground, the faster orbital speed causes the Sun to briefly appear to reverse course and move backward across the sky. Then, about 4 Earth days after perihelion, the planet's rotation once again dominates the motion, and the Sun's normal forward movement resumes. This bizarre phenomenon, which occurs twice a day on one of Mercury's poles, is a stunning demonstration of celestial mechanics at work. One final detail about Mercury's orbit is its axial tilt, or obliquity, which is the angle between its rotational axis and its orbital plane. Mercury's axial tilt is almost zero, with the best measured value being an incredibly small 0.027 degrees. This is even smaller than the tilt of the gas giant Jupiter, which is measured at 3.1 degrees. This minimal tilt means that the poles of Mercury receive almost no change in solar illumination throughout its year, helping to sustain the permanently shadowed regions where water ice can survive. It is also important to note that Mercury's orbital plane is inclined by 7 degrees relative to the plane of Earth's orbit, known as the ecliptic. As a result of this inclination, we can only observe Mercury transiting passing directly in front of the Sun when it is precisely aligned on the same node, the point where the two orbital planes intersect, as Earth. Because of that 7 degrees tilt, a transit only happens roughly once every 7 Earth years. To conclude our discussion of Mercury's place in the solar system, we can look outward. The MESSENGER probe captured a final image looking back toward Earth, showing our home planet as a tiny, multi-pixel speck. In that single, faint image, captured millions of kilometers away, virtually every single person on Earth, save for the youngest newborns, was contained within those few pixels, a powerful reminder of the enormous distances and quiet scale of the universe we are exploring. To understand the significance of the MESSENGER mission, we must start with context. When humanity first began sending probes to explore the solar system, the initial targets were Venus, our closest neighbor, in 1962, followed by Mars in 1965, and then the distant giant Jupiter in 1973. Only after these did we send a probe to Mercury in 1974. This sequence seems counterintuitive. The closest distance between Earth and Mercury is approximately 77 million kilometers. In fact, Mercury is, on average, the closest planet to Earth. By comparison, the closest approach between Earth and Jupiter is 588 million kilometers, nearly 8 times farther. Yet, Jupiter saw multiple subsequent visits, again in 1974, twice in 1979, and then in 1992, 1995, 2000, and 2007. Numerous missions were also launched to Saturn, Uranus, Neptune, comets, and asteroids. While Mercury received no attention for over 30 years after its initial visit. Was this neglect due to a lack of interest? Did that single first mission, Mariner 10, discover everything there was to know about the planet? Absolutely not. Mariner 10 was a flyby mission and only managed to map approximately 40% to 45% of Mercury's surface. The real reason for the extended delay is that Mercury is arguably one of the most challenging planets to visit in the entire solar system. As previously discussed, Mercury exists in a literal solar furnace. Due to its extreme proximity to the Sun, its daytime surface temperature routinely soars to highs of 430 degrees Celsius, 800 degrees F. Any visiting probe requires immensely sophisticated and robust heat shielding to survive. However, the major hurdle is not just the heat, it is the Sun's gravity. Any probe launched toward Mercury naturally accelerates faster and faster due to the Sun's immense gravitational pull. Using conventional rocket fuel to fight this acceleration would be the equivalent of trying to swim against a raging whitewater rapid. Combating the Sun's gravity to slow the spacecraft down enough to be captured into Mercury's orbit required an enormous amount of fuel, far more than a typical space probe, such as a Discovery-class mission, could afford to carry. The core scientific problem was that slowing the spacecraft sufficiently to enter Mercury's orbit seemed impossible given the constraints of rocket science and engineering at the time. The entire problem boiled down to weight. Weight is a critical and constant limitation in spacecraft design. The heavier a craft, the larger the rocket required to launch it out of Earth's orbit, and the exponentially higher the mission cost. To mitigate these expenses, scientists strive to keep every component as light as possible. Since fuel takes up precious weight allocation that could otherwise be used for scientific instruments, engineers only take the bare minimum necessary for trajectory corrections. For nearly 3 decades after Mariner 10, scientists could conceive of no way to put enough propellant on a probe to achieve orbit around Mercury while still including the essential scientific equipment. Following the success of Mariner 10's flyby missions in 1974 to 1975, Mercury exploration was effectively put on a long hold. This technical deadlock finally broke in 1985, thanks to an orbital mechanics expert named Chen-Wan Yen. She realized that there was a feasible trajectory for an orbiter that did not require radical new technology, but instead relied on clever, existing physics. Her calculations determined a specific, highly choreographed route through the inner solar system that would use gravity assists, speeding up or slowing down by flying past planets to decelerate the probe enough to be captured into Mercury's orbit with only minimal course corrections needed from its onboard thrusters. The solution was not to go directly to Mercury, but to take an incredibly long, winding way around. Under Chen-Wan Yen's model, a spacecraft would orbit the Sun approximately 15 times, utilizing flybys past Earth once, Venus twice, and Mercury itself 3 times before finally slowing down enough to execute the orbital insertion maneuver on the 4th pass. These planned planetary flybys would be absolutely essential. By skimming the atmospheres or gravitational fields of these planets, crucial speed could be gradually shaved off through atmospheric drag. Minimal, but helpful, and, most importantly, through precise gravitational maneuvering. The total route would cover a mammoth 7.9 billion kilometers and would take 6.5 years to complete. Chen-Wan Yen's groundbreaking findings were not immediately acted upon. However, by 1998, NASA began taking serious interest in the feasibility of the route. After confirming the model's viability, the space agency greenlit the mission and launched the Messenger probe in 2004. MESSENGER, the acronym for Mercury Surface, Space Environment, Geochemistry, and Ranging, was a remarkably compact craft. It measured only about 1.88 meters long and 1.3 meters wide, and weighed approximately 1,100 kilograms. This size and mass were small and light for a typical NASA mission. For comparison, the Juno probe sent to Jupiter is about 20 meters long. Messenger came equipped with a powerful main thruster, a specialized ceramic fabric heat shield to protect its instruments from the intense solar radiation, 2 large solar panels, and a comprehensive suite of scientific equipment designed to image and measure data from Mercury. The scientific team had clear objectives: to seize this rare opportunity to learn as much as possible about the chemical composition of Mercury's surface, its geological history, its mysterious magnetic field, and the structure of its dense metallic core. Messenger's first year in space was dedicated to making one full orbit around the Sun before meeting back up again with Earth for its first gravity assist. This maneuver provided a critical opportunity for scientists to test all the onboard equipment on a known astronomical body. They could check for any errors in the instruments, confirm data accuracy, and make any necessary software or hardware adjustments. Messenger took high-resolution photos of both Earth and the Moon and successfully tested its other instruments by taking readings of our atmosphere and magnetosphere. Fortunately, all systems were found to be working perfectly. As the probe began to head further sunward, it employed a clever, passive technique to help reduce its acceleration toward the Sunday. It used its large solar panels not just for power, but also to catch solar radiation, much like sails on a ship catch the wind. Solar radiation, the constant stream of photons, actually exerts a very tiny but persistent physical push on any object it hits. While this force is extremely minuscule, because Messenger's journey was planned to be so long, the accumulated effect really added up. Maximizing the use of this phenomenon was one of the key engineering innovations that allowed Messenger to save precious propellant and naturally decelerate over its long, complex trajectory. The next major milestone in Messenger's journey was its first flyby of Venus in 2006. Unfortunately for the scientific team, this moment occurred when Venus was on the exact opposite side of the Sun from Earth. This meant Messenger was temporarily out of radio contact, unable to communicate. It did capture some important photos of the planet, which it later transmitted, but otherwise, it performed no dedicated science during this pass. However, in 2007, Messenger passed Venus again. During this second pass, another spacecraft was already in orbit around Venus, the European Space Agency's ESA Venus Express. The two missions took the unique opportunity to work together, performing the first ever simultaneous measurements of the particle and field characteristics of the planet's environment. After the Venus flybys, the probe's focus shifted entirely to the main event, Mercury. Messenger made its first flyby of Mercury on the 14th of January 2008, with all systems functioning smoothly. The same success was achieved during the second flyby, but during the third and final flyby in 2009, a serious problem arose. Messenger unexpectedly entered safe mode, an automated protocol designed to protect the spacecraft's critical systems in the event of a significant error. To have come so far surviving the heat, the radiation, and the gravitational challenges, only for the mission to potentially fail during one of the final deceleration stages, was a moment of intense stress for everyone involved. Messenger remained in safe mode for a tense 7 hours. The glitch occurred because the spacecraft was required to pass through Mercury's shadow during this flyby, meaning it had to rely solely on its batteries for 18 minutes. It turned out that something in the power management software had been improperly configured. Fortunately, the spacecraft's computer performed an automatic reset once the solar panels were once again exposed to sunlight and fully recharged the battery. Messenger was able to emerge from safe mode and continue its mission, swinging around the sun one more time before finally achieving the historic moment, entering orbit around Mercury on the 11th of March 2011. Upon achieving orbit, Messenger settled into a highly elliptical orbit around Mercury, alternating between a closest approach of 200 kilometers and a furthest distance of 15,000 kilometers. This specific orbital geometry was a crucial part of the spacecraft's heat management strategy. Mercury acts much like a colossal curved mirror, reflecting intense solar radiation back into space. Remaining too close to the planet for extended periods would have been too hot for Messenger, even with its primary heat shield, which was designed mainly to protect it from the sun's direct radiation, which is 7 times more intense at Mercury than at Earth. The 2-hour-long, highly elliptical path allowed the spacecraft to move farther away from the planet's radiating surface every half orbit, giving it a vital opportunity to cool down before its next close pass. Messenger spent the next 4 years in Mercury's orbit, vastly exceeding the scientists' hopes and original 1-year mission expectation. Before launch, the team had optimistically aimed for the probe to capture at least 1,000 photos over its lifetime. However, Messenger ultimately returned over 200,000 photographs, providing humanity with a complete, high-resolution color map of Mercury's surface, in addition to images of nearby comets and other planets. By the 25th of December 2014, the meticulously conserved propellant was finally nearing exhaustion. By this point, Messenger was skimming just 25 kilometers above the planet's surface. Scientists used the very last remaining fuel in a series of final bursts to slightly extend its orbital lifetime for as long as possible. But on the 30th of April 2015, after a journey that spanned over a decade and covered literally billions of kilometers, Messenger's mission concluded as it deliberately crashed into the surface of Mercury. Before its demise, Messenger provided a wealth of critical insights into Mercury. The spacecraft carried a host of scientific instruments, including a magnetometer designed to map out Mercury's magnetic field. This field is believed to be generated by a dynamo effect, the churning motion of electrically conductive liquid material within its large, molten core. On Earth, our fast rotation and the strong tidal forces from the moon help keep our core molten and the dynamo going. Mercury, however, lacks a moon and rotates very slowly, taking 59 Earth days for one rotation. So, what keeps its core churning and the dynamo active? What Mercury does have is the most eccentric orbit of all the planets. As it moves closer to and farther away from the sun's gravitational strength constantly increases and decreases. This variable gravitational force creates powerful tidal forces that continually pull and squeeze on the planet's interior. The resulting internal friction and stress generate enough heat to maintain a molten outer core and sustain the magnetic dynamo. Messenger data revealed 2 major points of interest regarding this field. Unlike Earth's magnetic field, Mercury's is significantly offset from the center of the planet by about 20% of the planet's radius. The exact reason for this substantial offset remains a significant question mark in planetary science. Furthermore, while the field is only about 1% as strong as Earth's, it is still powerful enough to deflect a substantial amount of the solar wind around the planet. However, because Mercury is so much closer to the sun, the solar wind pressure is considerably greater here than it is at Earth. Combining this higher pressure with Mercury's weak magnetic field means the planet's magnetosphere is compressed extremely close to the planet's surface. Earth's magnetosphere, by contrast, extends outward many times the planet's own diameter. These factors conspire to make Mercury's magnetosphere exceptionally dynamic. What does this entail? For one, magnetic reconnection events are estimated to be about 100 times more common around Mercury than they are around Earth. Reconnection events occur when the magnetic field lines, which are under immense stress as the charged solar wind constantly pushes against the magnetosphere, suddenly break and snap together. When this happens, it creates an opening that allows a small stream of charged particles from the solar wind to briefly break into the planet's magnetosphere, where they enter a region of energized gas known as plasma in the planet's magnetotail, the extended part of the magnetosphere that points away from the sun. The flows visible in plasma simulations are direct evidence of these frequent, small-scale reconnection events. Another feature of the magnetosphere that MESSENGER detected was sudden, intense bursts of energetic electrons that produce hundreds of thousands of electron volts of energy. As MESSENGER orbited Mercury, it picked up thousands of these events. Mysteriously, these energy bursts were primarily localized in the northern hemisphere and were highly compressed toward the planet along the sun-facing side. This remains an active area of study, but scientists hypothesize that these electrons are accelerated through rapid breakdowns in the magnetotail and then follow the magnetic field lines from the South Pole to the North Pole. MESSENGER was equipped with a wide array of spectrometers. These instruments are essential in planetary science because they allow researchers to detect the composition of mineral deposits on the surface without having to physically take a sample. Spectrometers analyze the specific wavelengths of light, either absorbed or emitted by surface materials, revealing their chemical identity. They can also be used to detect particles in the atmosphere. As mentioned, Mercury does not possess a true atmosphere, but it has a very thin exosphere. This exosphere is so tenuous that the particles within it rarely, if ever, interact or collide with one another. What MESSENGER discovered about the relationship between the exosphere and the surface composition truly surprised the scientific community. The data indicated that Mercury is covered with surprisingly high levels of volatile substances. It is not simply a uniform, baked, fried, rocky planet. Its surface appears to be rich in elements like potassium, magnesium, sulfur, sodium, and chlorine, present at higher overall levels than on any other interterrestrial planet and significantly higher than on our moon. The fact that Mercury's volatile ratios share more similarities with a distant planet like Mars than with its closer neighbors, Earth and Venus, completely undermined many of the existing solar system formation theories that were prevalent before MESSENGER arrived. Those theories generally predicted that the closer a planet formed to the hot sun, the fewer volatile elements it should retain. Mercury defied this expectation. These volatile elements are continuously being blasted by solar radiation. This radiation is more intense near the equator than near the poles, which may explain why some substances, like potassium, are observed to be more abundant in the planet's northern hemisphere than near the equator. It is much hotter at the equator, meaning the potassium there would have been heated enough that much of it was lost from the surface and injected into the exosphere. The exosphere itself contains many of the same particles found on the surface: sodium, potassium, and the other volatile elements mentioned. As established, this exosphere is far from stable. Solar wind constantly picks up and carries away many of the charged particles, and solar radiation pressure continuously pushes away many of the neutral particles. Were it not for the processes that constantly replenish the exosphere, Mercury would lose it all to space over a relatively short period of time. While most substances certainly originate from the planet's surface through sputtering and vaporization, the exosphere also contains other elements that cannot be found there, specifically hydrogen and helium. So, where do these elements come from? As you may know, the sun is predominantly composed of hydrogen and helium. The solar wind constantly carries these particles outward, and when it streams past Mercury, some of the solar wind particles are actually captured by the planet's weak magnetosphere and gravity. These solar wind particles get caught up in the exosphere and stay for a while. As far as scientists can tell, this capture of solar wind is the only major source of hydrogen and helium within Mercury's tenuous exosphere, demonstrating a direct, continuous link between the sun and the composition of its innermost planet. The continuous outflow of materials from Mercury's surface presents fascinating features. Messenger images captured light from calcium atoms in the exosphere, and through some mechanism that remains unknown, this element is significantly more prevalent streaming away from the planet during dawn than during dusk. Similarly, magnesium atoms were detected actively streaming away from the planet's night side. As we have discussed, this outflow of elements creates the planetary tail. In older images, specifically those highlighting the sodium ions, the light emission makes Mercury look distinctly like a comet, with the ions brightly illuminated as they stream away. Incredibly, if you were an observer standing on Mercury during its long night, you would actually see a faint yellow-orange glow along the horizon, reminiscent of city lights seen from a distance on Earth. This tail is also subject to seasonal variations. Mercury's eccentric orbit causes its distance from the Sun to change throughout its 88-day year, and its orbital speed also varies. Scientists have found that the time of greatest sodium emission is actually when Mercury is at its middle distance from the Sun, which optimizes the specific conditions for the Doppler shift to occur, maximizing the tail's visibility and apparent output. One other curious substance that scientists detected in Mercury's exosphere was completely unexpected: water vapor. This vapor could potentially originate from the tails of comets as they pass close to the planet, or, more likely, it is released from the surprisingly large ice deposits that Messenger confirmed around Mercury's poles. It seems paradoxical that water ice can exist on this scorched planet, but it does so only at the bottom of permanently shadowed craters. These regions, located deep within large polar craters, are tilted in such a way that they are forever protected from the direct interaction of the sun's powerful light rays. This constant, absolute shadow keeps the temperatures frigid enough to preserve the frozen water. The Arecibo radio telescope on Earth had previously detected highly reflective regions near Mercury's poles, and as messenger images came in, these highly reflective zones were confirmed to align perfectly with the regions of permanent shadow at the base of the large craters. Current estimates suggest the amount of water ice found on Mercury could be as high as a quadrillion kilograms, 1,015 kilograms. While this is not a massive amount compared to Earth's total water volume, it represents a significant and highly valuable resource that would greatly boost the feasibility of any future human colony on the planet. Messenger also revealed other highly surprising surface features. Small, irregular depressions, called hollows, were found dispersed across the surface. This is a unique feature to Mercury. These distinct pits are not observed on the Moon or other airless bodies. While scientists are not completely certain of their origin, the leading theory is that they are formed by highly volatile substances like sulfur compounds or chlorine sublimating, turning directly from solid to gas when exposed to the intense solar environment. They are unique to Mercury precisely because of its close proximity to the Sun, which drives this rapid, volatile loss. These hollows appear to be the result of a currently active geological process, representing some of the youngest features on the planet. Crucially, they are clearly not the result of meteor impacts, showing that Mercury's surface is dynamic and still changing today. Beyond these recent features, Mercury's surface holds the scars of a complex history, including ancient dried-up lava flows, clear evidence of earlier volcanic activity, and massive craters from asteroid strikes that briefly heated large areas of its crust. Surprisingly, there are also the thin, winding lobate scarps, the stepped ridges which are evidence of the planet's gradual cooling and interior shrinkage. These scarps show that Mercury is actively contracting. Data from MESSENGER indicates that the planet's diameter has shrunk by over 14 kilometers since its formation, which is substantially more than was expected. All these findings have profoundly thrilled scientists. Yet, despite the fact that our modern understanding of Mercury is almost entirely dependent on the MESSENGER mission, the public awareness of this mission remains relatively low. Perhaps the ongoing Bepi-Colombo mission, which is currently en route to Mercury and scheduled to arrive in 2025, will better capture the public's imagination when it begins its orbital phase. To understand Mercury's history, we must go back to a time when the planet was much warmer. At that point, a critical question arises. What happens when a planet melts? For Mercury, this is not a theoretical question. At the risk of understatement, Mercury is an incredibly hot planet, with daytime temperatures currently reaching an incredible 430 degrees Celsius, the temperature of some wood-burning fires. The rocks and dust on its surface are constantly baked beneath a blistering heat that pushes the materials toward their structural limits. While it is not the hottest planet, that title belongs to Venus. Thanks to its dense, insulating atmosphere, Mercury is certainly close to the extreme. The Mercury we observe today has actually cooled considerably over its 4.5 billion year history. The presence of ice at its polar caps and the signs of global contraction on its surface, which show that its interior has become colder and shrunken over time, confirm this cooling trend. So, what was the planet like in its youth? When rock is sufficiently heated, its solid crystalline structure breaks down, and it transforms into a gloopy, viscous liquid known as magma. Magma is characterized by its viscosity, or runniness, which can be 10,000 to 100,000 times more viscous than water. For a point of reference, its consistency is similar to that of thick tomato ketchup. Depending on the rock type, magma forms at temperatures ranging from at least 600 degrees Celsius up to potentially 1,300 degrees Celsius. Thus, for Mercury to have experienced widespread melting, we know its early interior must have reached at least these temperature thresholds. Despite being significantly less runny than water, magma once erupted onto the surface and called lava can still travel vast distances before hardening. This is because once the surface of the lava cools, it forms a solid, insulating crust that protects the still molten material beneath, allowing the liquid to continue flowing freely over large distances. How do we know this widespread lava flow happened on Mercury? The clues are clearly visible within its craters, such as Raditlati. Scientists estimate that Raditlati is a relatively young crater, likely less than 1 billion years old, with well-preserved, sharp walls and a floor that is comparatively clear of other later impacts. It is also large, over 250 kilometers in diameter. When you look at this feature, notice how rugged and hilly the terrain is around the crater, yet the interior floor is remarkably smooth. This smoothness is not coincidental. Originally, the terrain inside Radat Ladi was likely just as rugged as the surrounding hills. It is smooth now because of lava. When lava is deposited on a surface, the liquid material, dragged down by gravity, seeks to form the flattest surface possible, just like water filling a bowl. In this case, an asteroid crashed into the planet's surface, and the resulting basin quickly filled with lava. Once the lava cooled and solidified, it formed the perfectly smooth plain we see today. But where did this lava originate? There are two primary theories. The first is that the immense energy from the meteor impact triggered a volcanic eruption, causing magma from beneath the surface to rise up through cracks in the crust to fill the basin. The second explanation is that the surface rock within the crater got so incredibly hot from the kinetic energy of the impact that it pushed the already hot rock crust over the melting point. This type of melt is known as impact melt. The true explanation for many features is likely a combination of both processes. Once we recognize that surface smoothness is a telltale sign of ancient lava flow, we immediately notice numerous other craters on Mercury that must have similarly been filled with lava. Examples include Rustaveli, where rugged mountain peaks can be seen poking up through the smooth lava layer, or the craters Copland, Polygnotus, and Rachmaninoff. Rachmaninoff is particularly interesting because it shows strong indicators of lava bubbling up from beneath the surface toward the crater's center. Notice the strange, crinkled cracks forming a rough degrees inside the central crater. Such features signal a slower, more controlled outpouring of magma that pushed up from beneath the surface, fracturing the cooled plain, rising slightly, and then cooling again under the effects of Mercury's wildly fluctuating temperature. In Rachmaninoff and many other similar impact craters, the violent collisions from space acted as triggers, initiating deep-seated volcanic activity from within Mercury's shell. Lava, however, did not just flow within craters. Take a look at the feature known as Angkor Vallis, or Angkor Valley. Here, you can see clear signs of a smooth lava flow, but this time, moving like a river. The lava traveled from high ground to low ground until it eventually poured into the basin next to it. Flows like these eventually filled massive seas or plains, taking up vast swaths of the planet and resulting in the more orangey color we see in certain regions today. Scientists have begun to recognize this telltale orange-red color as a reliable sign of major volcanic activity. From this evidence, a more detailed and considerably less hospitable picture has emerged of conditions on early Mercury. Areas like the region to the northeast of Rachmaninoff are almost certainly formed by volcanic activity. When Messenger flew over this area in 2015, it took detailed photos and found the surface to be covered in a very fine dust. Upon careful review, scientists realized this dust was volcanic ash that must have explosively fired out of surface vents and covered the terrain around the vent. NASA scientists vividly likened it to a form of snow, but a fiery, hot, angry snow. This means that an early inhabitant of Mercury would not only have had to contend with lava flowing beneath their feet, but also with burning ash falling from the sky. The final indicator of volcanic activity on Mercury hints at eruptions so destructive that entire chunks of the planet were carved out. Consider the crater Navoy. This feature is not an impact crater. When a crater is formed by a meteor strike onto a hard surface, one that is not hot enough to melt into lava, a central peak is usually formed. This happens because when the crater walls are suddenly exposed, the planet's gravity exerts itself on all the loose material, which rushes down the sides toward the newly scooped out basin's center. Once there, having built up momentum, this material collides violently with the rock and debris sliding down from the other side. This tremendous energy and momentum force the material to keep moving in the only direction possible, up. You can see the same effect more clearly when you throw a large rock into a calm body of water. The water rushes in to fill the gap, crashes in the center, and a powerful secondary splash shoots upward. Unlike water, however, the sand and loose rock of a crater floor do not level out, but solidify, forming a central peak. The shape of this peak depends on the impact angle, sometimes perfectly rounded, sometimes teardrop-shaped. However, the central formation of Navoi is neither a rounded nor teardrop-shaped peak. Scientists concluded that this feature was not formed by an impact at all. Instead, it had been carved out solely by the force of an erupting volcano. At 66 kilometers in diameter, the amount of force exploding upwards necessary to carve out this enormous crater and scatter its remnants for kilometers around must have been truly massive and catastrophic. So, there we have the picture. Meteors raining from the sky, tipping the rocks they landed on over the melting point. Volcanoes bursting forth, either filling the landscape slowly with bubbling magma that formed lakes and fiery rivers, or choking the surrounding areas with burning ash. And even the ground you stood on could, at any moment, explode violently under your feet. This is the hellish reality of what it was like when a planet was melting. Mercury is quiet now. As far as we can tell, there are no longer any truly active volcanoes erupting on the planet's surface. Although the sun still relentlessly bakes down on it, the fierce, unbridled geological fury that once raged beneath its crust is now largely calm and soothed. Yet, for those who possess the tools and knowledge to look, the undeniable evidence of what once was remains locked deep within its geological record. It is the scars, the ridges, and the craters that tell the profound story of a violent and dynamic past. Because Mercury is so incredibly difficult to reach, it is exceptionally tricky to study closely. This difficulty explains why, in all of human history, there have only been 2 completed missions to Mercury: Mariner 10 inches, 1974, and Messenger in 2011. A third mission, Bepi Colombo, is currently en route and scheduled to arrive in 2025. Of the 2 missions completed, only Messenger went into orbit around Mercury, and thus it remains the only mission to ever provide us with complete, close-up, high-resolution maps of Mercury's diverse surface. Surprisingly, more than a decade after Messenger's successful orbital phase, some of the formations seen on the surface remain unsolved mysteries, while others provide powerful hints about the raw, primal energy that shaped the early solar system. Let us conclude by examining some of those surface mysteries and formations to see what clues and tentative answers we can find. When you first view a full-color map of Mercury's surface, a few features immediately stand out. First is its color. Mercury is not the uniform gray sphere of the moon. Instead, it is patterned with speckled grays, creams, and beiges, featuring distinct lighter and darker sections and lines. The prevailing hypothesis regarding the dark material involves graphite, a form of carbon. Scientists believe that during Mercury's initial formation, when its mantle was still molten and much of the planet's internal chemistry was sorting itself out. Light, carbon-rich compounds floated to the top of the magma ocean. As the planet cooled and the crust solidified, this carbon layer was either near the surface or eventually brought to the surface by geological processes like massive impacts. Subsequent impacts have continuously pulverized this carbon layer, turning it into a fine, dark powder. These darker sections are generally believed to indicate high concentrations of this primitive graphite, suggesting that Mercury's original crust may have been entirely carbon-rich. The lighter sections, however, are a separate mystery that connects directly to the mechanics of impact events. Beyond the color variations, the most noticeable features are the craters. Much like the Moon, Mercury is thoroughly covered with craters, formed as ancient pieces of space debris continuously crash down onto the unprotected planet. These impacts are distributed roughly evenly, offering fascinating insights into the planet's violent history. The age of a crater can often be inferred by the condition of its rims. Sharp, crisp rims suggest a much more recent impact, as they haven't had much time to degrade. Older craters display rougher, more worn-down rims, eroded by the slow, natural processes happening on the planet. Asteroids sometimes strike within the same location as previous collisions, creating overlapping craters of different ages, clearly illustrating the passage of time. It is in the difference between these older and younger craters that we find our first fascinating clue about the surface of Mercury. It is not entirely static. Although there is no thick atmosphere to produce the weathering we see on Earth, things on Mercury's surface do not remain fixed on an astronomical timescale. The changes observed on Mercury are driven by two main forces: the relentless, slow forces of internal cooling and the occasional catastrophic energy of external impacts. As previously discussed, Mercury is constantly cooling and contracting. The dense, metallic core is shrinking, and as it does, the outer crust must adjust to the smaller volume. This stress causes the crust to fracture and buckle, pushing layers of rock over one another. This movement is responsible for the formation of the kilometer-long lobate scarps, the thin, linear ridges that crisscross the surface. The extensive network of these scarps across the entire planet underscores the fact that this contraction is a global process, confirming that the planet's overall diameter has shrunk by that significant 14 kilometers. This degree of global contraction suggests that Mercury's interior was much hotter and larger earlier in its history than previously modeled, forcing scientists to rethink the thermal evolution of the inner solar system. But Mercury's surface is not just shrinking. It is also subject to other subtle erosion forces that cause it to smooth out. This subtle erosion, known as space weathering, is caused by the constant bombardment of micrometeoroids and high-energy particles from the Sunday. These processes slowly grind down the sharp edges of older craters. In addition to this weathering, scientists have observed geological instability known as mass wasting or slumping. In one particular crater, scientists observed clear evidence of slumping having taken place. While about 90 degrees of the crater wall managed to retain its original, sharp shape, the remaining 270 degrees of the rim had slipped or collapsed further into the crater bottom, breaking away from the rest of the rim under the force of its own weight. This is a dramatic example of gravity acting on loose, pulverized surface material. Scientists are not entirely sure why this slumping occurred only to a portion of the crater and not the entire degree's umbrance. Was the ground composition particularly weak or fine-grained in that specific area? Did the angle of the original impact cause a subsurface weakness in that exact region that only gave way years later? Did the extreme temperature cycling hundreds of degrees swing every 2 Mercurian years cause thermal stress fatigue in only one part of the rim? These are the nuanced questions that remain open. This puzzle is precisely what makes Mercury so intriguing. There is still so much more to discover, even in the seemingly simplest features. Another interesting phenomenon on Mercury is the crater rays, or ray systems. These spidery, linear patterns radiate outward from certain impact sites and are a prominent feature of Mercury's surface, with some stretching over 400 kilometers across. Their lighter color is a key signal. It indicates that the material kicked up from beneath Mercury's surface is either less graphitic or possesses a different chemical composition compared to the dark, sun-exposed surface material. When an asteroid impacts, it excavates material from below the graphitic surface, revealing lighter, less space-weathered rock underneath, which forms the luminous rays. For a time, scientists could not explain the specific, linear pattern of these rays. When researchers attempted to recreate them in controlled hydrocode simulations and physical laboratory experiments testing different weights, terrain consistencies, and impact speeds, they consistently failed. Whatever they tried, the material they kicked up would always fall back down in a uniform, degrees-Euler blanket, never in the thin, radial spiderweb lines seen on Mercury. Scientists struggled with this mystery for years, suggesting the need for exotic physics or complex atmospheric interactions. The solution finally came in 2018. A scientist named Tapan Sabadia was searching the internet and discovered that a group of students had actually managed to recreate the spidery line pattern of crater rays in a simple experiment. Sabadia was both excited and confused. Why were these students able to succeed where specialized scientists had failed? He realized the key lay in a common practice. Scientists had been too neat. Before performing their tests in a controlled lab setting, researchers, including Sabadia, had always painstakingly smoothed out the sand that their test asteroid was impacting. The students, however, had skipped this preparatory step, leaving the test surface rough and heterogeneous. As it turned out, the natural roughness of the surface was the entire key. The initial, uneven surface causes the ejecta curtain, the sheet of material thrown out during the impact, to break up into distinct filaments as it travels. These filaments then deposit the material in the characteristic radial lines we see. This means that crater ray formation does not primarily depend on the speed of the impact, the angle of the strike, or the specific composition of the crust. They only care about the existing surface shape and how rough it is. Knowing this fundamental principle behind ray formation fundamentally alters our perception of the scale of impacts that have struck Mercury in its past. Remember that some of these ray systems stretch over 400 kilometers. Now, consider the rays originating from the crater known as Hokusai. These lines must have been created by an impact of incredible magnitude, as their rays stretch almost entirely around Mercury's degrees umbrance, which is approximately 15,000 kilometers. Though not quite as large, the ray system originating from the crater Dur covers over 1,000 kilometers. While the Moon also has ray systems, they are typically smaller than these Mercurian giants. In fact, these massive ray systems are one of the main distinguishing visual features of Mercury, showing us that one of the formative processes that explains the planet's unique surface is powerful, persistent bombardments from space. Since the sun is so nearby, objects caught in its intense gravitational influence accelerate rapidly, and would crash into Mercury with far greater force than Mercury could produce with its own gravity alone. Mercury's own gravitational pull is so weak compared to the Sun that it cannot normally capture objects into stable orbits as moons. Instead, they are usually pulled past. This same intense gravity is, ironically, the reason why visiting Mercury is so difficult for spacecraft. However, Mercury's proximity means it acts as a target, intercepting objects before they reach the Sunday. Yet, even the explanation of colossal bombardment cannot easily account for our final surface formation. Take a look at the fascinating crater Apollodorus and its surrounding, striking network of troughs, known as Pantheon Fossae. The entire structure sits within the massive Caloris Basin, the 1,550-kilometer wide scar from a colossal, ancient impact. Apollodorus itself is a small, relatively young crater. There are numerous linear fractures radiating out from its center. The entire network of troughs, the Pantheon Fossae, bears a strange resemblance to fractured glass. Glass fractures in this way because of its hard, brittle qualities. Most other craters we've observed on Mercury do not follow this pattern. The crust usually either sprays outward in ray systems or forms simple, perfectly round craters, consistent with a looser material makeup. Sand, after all, does not fracture when hit. We do not see this specific kind of linear fracturing anywhere else on the planet, suggesting something unusual occurred here. The composition of the crust here could have been particularly cold and hard when a stress event occurred, making the crust more brittle. Mercury's night side can indeed reach temperatures as low as -180 degrees Celsius. But if cold temperature were the cause, why has this pattern not been observed elsewhere? When we look closer at Apollodorus, the crater often assumed to be the source of the fractures, we notice something even stranger. The crater is not quite the epicenter of the entire fracture network. While it is very close, it does not perfectly line up with the exact center point of the radiating lines. This suggests that Apollodorus and the spidery fractures of the Pantheon Fossae may actually be unrelated. If the impact crater isn't the cause, what created the vast, fractured glass shape of the Pantheon Fossae? The leading theory links the structure to the immense Caloris Basin itself. The colossal impact that created Caloris caused a massive disturbance that rang through the entire planet. One hypothesis suggests that the tremendous weight of the lava and impact melt that filled the Caloris Basin caused the crust beneath it to sag. This sagging created enormous tensional stresses at the center of the basin, pulling the crust apart and causing the radial fractures we see today. The Pantheon Fossae, therefore, would be a giant tensional fault system, evidence not of a meteor strike, but of the crust stretching and failing under the weight of the largest impact basin on the planet. Evidently, something created this fractured glass shape, but left no large, central impact crater. Does that imply this feature is the result of forces not hitting it from above, but rather pushing its way up from beneath? The tensional fault theory suggests the crust was pulled apart from the sides. Another, less favored, hypothesis suggests a large volcanic dome or a plume of magma pressed up forcefully from the deep interior, causing the radial crack pattern before the magma subsided. That remains only a hypothesis, one of many possibilities that scientists continue to explore. Despite the wealth of data provided by the Messenger mission, Mercury's surface still holds countless mysteries that challenge traditional solar system models, leaving scientists with profound questions. Why did Mercury, the planet closest to the Sun, retain such surprisingly high levels of volatile elements like sulfur and chlorine? defying theories that predict such substances should have been vaporized early on. What sustains Mercury's weak magnetic field through an internal dynamo? And why is this field so drastically offset from the planet's center? Furthermore, what is the precise chemical state of the water ice hidden within the permanently shadowed polar regions? And how much of this ice is actively being lost or replenished by the constant bombardment of the solar wind and micrometeoroids? These remaining enigmas underscore why the ongoing Bepi-Colombo mission is crucial to advancing our understanding of this unique terrestrial world. When ESA's Bepi-Colombo mission arrives at Mercury in 2025, it will begin another extensive study of the planet. Bepi-Colombo carries a suite of instruments specifically designed to address these core mysteries. It will provide the first magnetic field data for the southern hemisphere, offering a complete picture of the dynamo. Its more sensitive spectrometers will refine the volatile element inventory, and its sophisticated orbital path will allow for detailed, continuous monitoring of the exosphere and the famous sodium tail. Perhaps then, we will have the data necessary to provide definitive answers to the riddles of the Pantheon Fosse and the planet's high volatile content. For now, Mercury endures, baked in its solar furnace. It has survived for billions of years and will likely survive for billions more, despite the constant fury that the sun and the rest of the solar system throw at it. The hellish conditions of its environment make it challenging to reach, but there is no denying its resilience, which is visible in its charred, cratered beauty. Perhaps one day we will know all there is to know about the first planet in the solar system. But that day is not yet. In spite of it being the most illuminated planet in the solar system, there is still plenty of light left to shed on Mercury.